whole run of T-shirts. I think we sent them to China, where they didn't read much English anyway. But it was the line. Correct me if I'm wrong. Was it is easier to invent the future than it is to predict it. And Alan has been out inventing the future for the last 30-odd years or more in computing. And the thing that is particularly exciting is he very much agrees with my point of view when he says it hasn't really happened yet, even now, despite all the wonderful things that have happened over the last decades. We're just at the beginning of the computer revolution, and he's going to talk to us about his latest thoughts on that subject this morning. Alan, thanks very much.
Thank you. Thanks. So this talk starts off with a little old fartism. I'm now old enough so I can get away with it. I was an old fart when I was in my 20s, but now I'm officially one, which is a little bit of complaining about where we are and what hasn't happened. Pay tribute to a few things that were done a long, long time ago. It's always nice to remember those. Show you some ideas about how to make things better, trying to get you interested and enlist you in this thing. And then at the end of the talk, we want to show you some pre-alpha software that we think is pretty darn exciting. And so with that, my first complaint is that the last 20 plus years or so have been pretty darn boring. And I think it's partly because when personal computers got commercialized, a lot of the vendors aimed at business, and businesses just aren't that creative about using any kind of tool. Like most people in the world, they're an example of instrumental reasoning. And like most adults in the world, they're prime examples of learning a system and sticking to it. So my belief is the way to get ahead here is to think a lot more about children, and just to realize that the actual printing revolution wasn't the invention of the printing press by Gutenberg, but happened 150 years later when nobody who had invented the printing press was still alive, but it was done by the children who grew up in a world in which printing was used mostly for looking backwards, printing Bibles, arguments about religions and so forth. Gradually realized that the printing press could be used for a different kind of argument. And that kind of argument was what we call modern argument. And that brought in the 17th century modern ideas about how we argue about politics and how we argue about science in the real world. So I think the same thing is going to happen. Now, it's not that in the middle of the 15th century that there weren't people who didn't understand what the printing press was good for. But these were people who were very much in the minority. And it took this adoption by children for the general run of folks to make the printing press something interesting, something important. Now, in the parallel idea, it's 40 years ago that Project Mac first got funded by Lick here, Licklider, known as Lick. And a few years earlier, he had written in a very influential paper as a psychologist who studied perception. He wrote in a paper called Man-Computer Symbiosis that in not too many years, human brains and computing machines will be coupled together very tightly, and the resulting partnership will think as no human brain has ever thought. And if that was Lick's goal, and it was, and if that was the goal of ARPA, and it was, then we have to look around today and say, boy, that coupling hasn't happened yet. It's happened in science. Computing has absolutely revolutionized science. And the coupling of scientists and computers are indeed thinking as no human brain has ever thought before. But for the general mass of people who have computers, no such thing is going on, because most people are basically instrumental reasoners. Instrumental reasoning is the most dominant form of human reasoning, and it's the judgment of any tool or idea presented to a person solely in terms of the current goal structure of that person. That's what instrumental reasoning is. And the idea is accepted or rejected based on whether this new thing contributes to the current goals. So this is a real problem. Basically a good first order idea, terrible second order idea. And then the second thing, as I mentioned, is that adults basically have way too much context. So there's an enormous number of things that already work pretty well, and pretty well is the enemy of qualitative improvement, and vice versa. So these four goals were started on pretty nicely by ARPA, and just because it happens to be 2003, Ivan Sutherland published his thesis on Sketchpad in 1963, so it gives me yet another excuse. I always try and play this for people. So this computer that Ivan was on was almost as big as this entire floor. It's an air defense computer. You can see him at the console there. And the display could not even draw lines. The display could only plot points. So every part of this was done by Ivan. You notice he just pointed at the thing that he drew and told it to make all of the lines mutually perpendicular. You can see it has the first clipping window in history. And he's actually drawing on a canvas that's about a third of a mile on the side. So it's an infinite zoom interface, the first one. He just told those two guys to make themselves parallel to each other. Now the constraint is collinearity, as it draws these little dashes. So Sketchpad is kind of like a nonlinear graphical spreadsheet, in that it gathered together and was constantly exercising both the direct things that you did and the indirect rules that were part of the drawing. And when Ivan looked at this really awful display on the TX2, which had turned many other people away, he asked the question we all should be asking, which is, what else can it do? And the answer to him was it can actually simulate the details of drawings. It's not just something where you might do a replacement for a drafting tool, but something where you can actually put in models. So again, he says, make all of these guys mutually perpendicular. Notice that drags the center guys, and the cross point was used as the center of the arc of the circle, so he gets a nice little rivet here. And now he's showing that with slightly different initial conditions and the same rules, you'll get a different solution to the problem. And of course, you can constrain them to be multiples of each other. So it's got a little rivet here. And here's another really interesting thing about Sketchpad in 1963. Is you can get instances. So this is an instance of that rivet. And the instances are rotatable and scalable. So it's going to, you see this led to a desire for better displays. About half the capacity of the TX2 is actually used to maintain the display. So he's got a rivet in there, and now he's going to show, hey, but we can have multiple instances, because graphics and most things in the world are about multiple instances of ideas, which he called masters. Then he recognizes, whoops, I forgot about this cross piece, so I'm going to go to the master here and make the crossbars transparent. He comes back out to the drawing here, and he sees that all the instances have felt that change. So this is the first object-oriented software system that I know of. And in fact, it was kind of a prototyping system because he just constructed a flange with a rivet in it, and now he says, okay, make that be a master. And now let me make some instances of that new thing. So everything in Sketchpad was constructed this way, including the numbers and the letters, even a little text editor done in here. So one of the most incredible pieces of work in history done in 1 year by one person in machine code on a half-MIP machine the size of a building. So I once asked Ivan, how is it possible for you to have invented computer graphics, done the first object-oriented software system, and the first real-time constraint solver all by yourself in 1 year? And Ivan said, well, I didn't know it was hard. So he had this tremendous advantage of not having any context before him. And you should read his thesis. You can get it as a PDF file from MIT libraries for like $5 or $6. It's really worthwhile reading because not only is it probably the closest thing to an act like Newton did in the 17th century in our field, but it is wonderful for the number of apologies Ivan makes because it wasn't better. He wanted to do the whole thing. So this was, in many people's minds, for those of us who started doing stuff in the 60s, was the paradigm. We called this picture here when there was only one personal computer. That was Ivan Sutherland at the console of the TX2 from 3 o'clock in the morning to 6 o'clock in the morning while he was doing this, because the rest of the time it was used for air defense. Now, at the opposite end of the scale, also at MIT and also in 1963, was the advent of the PDD-1, which showed up in 62. And this was the first real mini-computer, a truly wonderful machine for anybody who's tried it. Had a much nicer display on it, and very quickly people started doing things on it. One of the things was called expensive typewriter, which was the first graphical text editor. And then very quickly, Steve Russell, who I'll talk about in a second, decided to implement Doc Smith's Lensman ideas for Space War. And this is kind of what it looked like here. So you had this circular display, and the spaceships obeyed F equals ma, and so you had to swing them around if you wanted to stop them. And so forth. So this game made a huge impression on people in their 20s back then. It was easy to implement if you knew a little physics. Every time a computer with a graphics display on it sprang up, somebody would do a version of Space War. It required the notion of objects, even though they weren't quite around yet, because you had multiple spaceships and you had torpedoes, and the darn thing was fun. So it had all of those elements of a revolution in the making. So that was 40 years ago. An accomplishment of a completely different sort, maybe the most profound thing, single thing done in programming languages, was the invention a few years earlier by McCarthy of Lisp. And his invention of it was a meta-invention. So this is kind of the Maxwell's equations of programming language here on the bottom of page 13 of the Lisp 1.5 Programmer's Manual. The anniversary we're celebrating today is the 40th anniversary of the implementation of this in an interactive form on the PDP-1. It was done by Peter Deutsch when he was only 16 years old. And it was one of the most beautiful programs ever written. So beautiful that the entire machine code was made part of a paper that he wrote about how he did it. So it became a kind of a paradigm for getting essentially the ultimate computer power you could get from a programming language in the sense of meta structures and flexibility And this language was the first time a programming language had been made the operating system of the machine as well, which I think is an idea that isn't paid enough attention to. So 40th anniversary of that. Then 5 years later, and it's great to see Stuart Brand in the room here, who when he was running the Whole Earth truck store and catalog right across the street from SRI, where Doug Engelbart was doing his stuff, actually was the one of the cameramen for this incredible demo that Engelbart did in San Francisco in 1968. I'm just going to show you a couple of excerpts here. So this is the setup that he had. This is a picture that was taken in the 60s. It looks completely modern. This is why I think Engelbart is the true father of personal computing, because what we call, so sound please. Sound.
So here, I'm afraid I'll need to... So I can say, I'd like to go to produce, but I'd like to go to produce, they get big, I'd like to say one branch only, and let me look just that low, and I see it. Oh, I can say, I'd like to see one line only. I can see it. But there's another thing I can do. There's a root I said I have here. So here, I'm afraid I'll need a different picture of the view. So here's what I drew with a picture drawing capability here. It's a slight map if I start from work, and here's the route I seem to have to go to pick up all the materials. And that's my plan for getting home tonight. But if I want to, I can say, the library, what am I supposed to pick up there? I can just point to that, and oh, I see, overdue books and all. Well, there was a statement there with that name on it. Go back. What am I supposed to pick up at the drugstore? I see, very interesting. All right. Market can do things if I want to just say, I'd like to interchange produce and canned materials. Bingo. And they're all numbered rightly if I care to look. Interchanging them very quickly. Cans are going to get interchanged with produce. They do it and all gets renumbered. Set it up so I see it over like that leaves a corner up there, and I say, now computer, do the automatic switching that'll bring in a camera picture from the camera mounted on his console, such as the camera mounted on mine is. Hi, Bill. That's great. Now we're connected audio. You can see my work, you can point at it, and I can see your face, and we can talk. So let's do some collaborating.
Go off to a directive file and see what the directive is to get Roman numeral page numbers. I'm into the file now. Here's the first level of the hierarchy. Let's open up page formatting. We look, we want page numbering, so we'll open that up. We find, yes, here it is, Roman numerals. We find out the directive. Yep, your bug's right on it already, Doug. Here's the directive we want. So we work down quite a way into a hierarchy, as you can see.
That use it for when they're conferencing in a room. They'd each have their monitors in front of them. They'd have their shared cursors on a screen. And this is part of the way of life back at SRI in 1968. Perfectly possible to do it for the last 20 years, obviously. Okay, so for me, very quickly, 66, I ran into Sketchpad and Simula, and I had a biological background, and that led to the idea of dynamic objects. I started working on a desktop machine, looked like this. It's a picture of it on its own display. A little bit later, I was influenced by this incredible pen-based system, 1968 at RAND. Take a look at this.
First we erase a flow arrow, then move the connector out of the way so that we may draw a box. The printing in the box is being used as commentary only in this case. The box is slightly too large, so we may change its size. Then draw a flow from the connector to the box. Attach a decision element to the box and draw a flow from it to scan. We then erase the flow arrows attached to the process post new area and move the box to a new position. This allows us to draw a new box.
So 1968, you might wonder why can't we do that on our handhelds? And the reason is that nobody is even thinking about this stuff. Of course we want to do stuff like that. By the way, that recognizer, which was done by Gabe Groner in 1966, was better than graffiti is today. It's written up in a paper for anybody who wants to read it. But of course our field doesn't read anymore, do we? So also in 68, I saw the first flat screen display, and Seymour Papert. And Papert had started working with children and discovered that children could actually learn differential geometry. So go forward 5, turn 5 over and over again gives you a nice little circle in Gaussian differential geometry. And that led to this idea that someday in the future, children would actually learn powerful ideas by building them themselves. To know the world, one must construct it. They learn it on these laptops that would be connected with wireless, and they make their own games of space opera. Now, 50 years from now, this is not going to be a weird picture to show. But in fact, there's been almost no effort of any kind by the general industry to try and... We've already gone through a couple of generations of kids without teaching them anything, even since the commercialization has happened. So we've got adults using computers today that are barely more able than they were 20 years ago. So if you look at this thing from a longer and wider point of view, the thing to do is to put a lot more effort into the systems that we do with children. Because children are the only people on Earth right now that do two-handed interfaces like Engelbart did. Right? Okay. And the main reason I show this is just to commemorate the 30th birthday of the Alto done by Chuck Thacker here that is kind of the prototype for most modern personal computing. For us, the Alto was a chance to get computers down in schools, and this problem of building interesting environments for children turned out to be by far the most difficult part of this problem. Okay, so here's some examples from today about what children do. I'm just going to do one little example here to show you the kind of programming that children do. The typical first thing they do is to, because they want to learn how to drive cars like adults do. So we say, okay, design yourself a little car and that you would like to learn how to drive, and just paint it in here. Both boys and girls like big, powerful off-road tires. This is a very typical... Because remember, not all children, just like not all adults, are actually interested in ideas. Many children really want to just prove that they're worthy to exist in the world, They feel unpowerful. They want to prove that they're powerful. They want to play role-playing games and so forth. So little object here. We can look inside of it. And the kids like this view of the object. We want them to love this view. Rename it car here. Car's heading says 0. I'll click on the caret here. The number counts up. We can see the car turning. And conversely, if I manipulate the car, you can see that number going positive and negative there. Behavior, car forward by 5. Each time I click on it, it goes forward. Car turn. Each time I click on it, it turns. If I want a script, I just drag out a tile, makes me a script, and click on the clock, and I've got a parallel script running. And in fact, I can steer the car by just clicking in here, and it's being recompiled dynamically as I change the things in here. Okay, that's sort of like kissing your sister, though, because what you really want to do is to do something like a steering wheel. So you paint a steering wheel. It's the same kind of thing as was before. I'll open it up and I'll call it wheel. And it's got a heading. If I turn it, see it goes positive, negative. I just saw the positive and negative numbers down here influence the car. That's an invitation to pick up the name of the numbers coming out of the wheel and just drop them in here. And now maybe I can drive the car. Now, this is kind of an interesting example of, well, what's the difference between this and the programming we do? Right? Why shouldn't all programming be like this? Good question to ponder on. Okay, so let's see some of the things that we do with this. Here's kids dealing with the physical world. We bring in a bunch of objects of different weights.
Objects that you think will fall to the earth at the same time. Okay. Do not pay any attention to what anybody else is saying. Just now. Who's got the apple? What do you get? What'd you get?
The timers, of course, don't work very well.
So put sponge balls.
I think we should do the shot put and the sponge ball because they're two totally different weights. And if you drop them at the same time, maybe they'll drop at the same speed. Drop.
So every class that has about 30 kids in it has one Galileo. This one was a little girl. You cut right to, she realized, nobody can click on and click off the stopwatches accurately enough because we don't know when the janitor is dropping the thing. So why not just drop them in pairs and listen for the result, which is basically what Galileo did. So the real way to understand what's going on here is to use a consumer video camera and just video what's going on. Even that's difficult to see. But because this is a dynamic media system with a uniform object model, we can just pull frames out of the movie, and so we can stack every fifth frame side by side, for example. We can stack them up vertically like that. And what the kids do is they start measuring from the bottom of the ball on one frame to the bottom of the ball on the next frame by just stretching these rectangles here. that, and then if you just stack these guys, so the heights of the rectangles are actually the measure of the velocity. And this looks like the velocity is changing by roughly a constant amount. And the little script for our simulated ball here says, let's take a variable called speed and increase it by -5 each time. So that's our constant acceleration. And then let's change the ball's position, vertical position, by that speed each time. And by the way, let's try playing it against, well, I'm going to stop right there and let Tyrone tell you what he did.
And to make sure that I was doing it just right, I got a magnifier, which would help me figure out if the size was just right. After I'd done that, I would go and click on the little basic category button, and then a little menu would pop up, and one of the categories would be geometry, so I click on that. And here it has many things that have to do with the size and shape of the rectangle. So I would see what the height is. I kept going along the process until I had them all lined up with their height. I subtracted the smaller one's height from the big one to see if there was a kind of pattern anywhere that could help me, and my best worked. So in order to show that it was working, I decided to leave a dot copy so that it would show
So it drops little cookies.
the exact right speed and acceleration.
To show it matches up with the video taken of the real ball. Here's another one where we run the simulation and the movie together, which is kind of fun. So by the way, understanding how this works is something that 70% of college students never get through successfully. So this is a good example of how point of view is worth 80 IQ points. Changing the context, changing the math, changing the way it's thought about, changing the way you make models has an incredible difference as to what you can do. We can thank Seymour Papert for many of these insights. Once you've captured gravity, you can put it on interesting objects, like a spaceship. And so you really want a motor. So gravity is a velocity eater, a motor is a velocity producer. This little script makes a flame when the motor is on, and this is the one that crashes you if you're landing too quickly. So you see I can toss the ship up here. Land it carefully. And you can go much further than that. So here's a little spaceship from Space War game. And I can get another one by just copying it here. Just trying to show you what these programs look like. This is the thing for Space War right there. Put these ships in here. Let's change the color of this one. Let's turn them on. This is kind of what we were thinking about. Stuart should find this interesting because this is a theme that he and I have been talking about for many, many, many years. Okay, let's shift gears to something a little more biological, which is feedback. Here's a little script I think you can all... It's fun doing this with programmers in the room because I don't have to explain this. Just read it. So the goal here was to make a car, a little robot car that would stay in the middle of the road. And this is the result, the solution of these two 11-year-old girls. So the idea is only go forward when you're sensing the blue color. Notice it stopped when it hit one of the curves. Turn one way or the other when you hit either of the curves. So it can negotiate any turn. They realized that if they drew the road poorly and all of these things were firing off, it would still work because the +4 and the -4 would cancel each other out. So this is a beautiful little solution. This was done by these kids after about 6 weeks of 1 day a week learning this stuff. it's quite shocking to see what children can do. So here's how you do animation. You make a bunch of drawings, drop them into the holder. The little program is holder's cursor increases by 1. What if I increase it by 2? What if I increase it by 0.5? You learn about rates and sampling. And then we're changing the costume of the ball. And if you combine that with the feedback and look at brightness, then you can do a salmon swimming upstream. So the salmon is trying to find the darker water, which represents a higher concentration of the perfume. And when it loses it, it's circling to find it. So it's chugging along here. And the clownfish uses the very same technique to follow the circular gradient given off by the sea anemone that it acclimates to. And if you take that idea and put it in the micro scale with a particle system like Star Logo, this is called Star Squeak, you can do ants. So we have 10,000 patches underneath here that are all computing simultaneously to do the diffusion of the pheromones given off by the individual ants when they find the food. And when an ant wanders into the gradient and it doesn't have food, it goes upstream to find the food. And once it has food, it follows another gradient to find the next. This is a wonderful thing for teaching children about systems. And I wish executives would understand it a little more also. Because you can see how simple local organizing principles can organize almost the entire system without requiring any direct communications. This is a loose coupling model. And there are more important things that children can learn about. For instance, they can learn about epidemics, such as the SARS thing or AIDS. This is a little 2-line program here, and these are just like the little cars infecting each other. Here's the survivor. But it's never been the case. So most infections that act slowly, have a very slow start, are not nearly as exciting as some of the other things. Okay, now now we're about ready for our experimental software. And this is pre-alpha stuff we're going to show you, so this might be a little more exciting. Or not. But David has been having some heating problems on his machine. We switched already? I'll switch. Yeah, so I'm over on that one, and David.
Can you see me over there?
Yeah, you're there.
Yeah, awesome.
So shall we try connecting?
Just a second.
So what this is a kind of a next layer on the internet. One of our colleagues is Dave Reed, who's the slash in TCP/IP. So there's another. It's a good way of saying it because he was instrumental in the separation out of those two ideas that are so useful today. And the basic idea here is that the internet itself was designed to solve an n-squared problem, which is how to do point-to-point communication without having a crossbar switch. So it's done using peer-to-peer. When it was done in the late 60s and 70s, it was realized that it was going to make Engelbart's immersive stuff really, really difficult. Because Engelbart's collaboration was done through a server, and there are unfortunately 2 to the n possible subgroups in a network of n people. So this is not a scalable idea. It's much less scalable than n squared. And so Dave Reed and other people started thinking about how could you do this 2 to the n problem as a completely peer-peer, non-server way of doing things. And so let's see if the demo guys are with us, David.
Okay. We are, I'm definitely over there?
Yeah.
Okay. What you're going to see here is, as Alan said, this is what I think of as a broadband conference call. And just to get things going, hopefully. Do you see anything happening on the right?
Yep.
Yes? No?
Yes, we do.
Oh, okay. No? Yes? Sage? Oh. He's there. I'm there. He's the bunny. I'm Alice. Yeah.
There we go.
Okay.
I'm now moving way out here, and I see Alice here, and Alice is going to the mirror here. So if you look over here, you can see what I'm seeing. So I'm just following.
So I'm looking at right now as a mirror, so I see myself and I see the bunny behind me. The mirror is essentially a portal, but it's a portal into the space we're in. It's actually this is like a little 3D window. I can turn that around like that, and again resize it, and pick it up and move it. It's probably the least interesting portal that you're going to see in just the next few minutes. Over here is our friend over there, but just to prove that looks like you see news. And then over here you have a little pyramid. Now what's happening is everything I do is shared over there with what he's doing. Essentially what we've got is a true shared space.
It's a replication architecture that's doing real-time transactions over the slow internet.
Right. And what's really cool about this is, in a sense, it's a late binding protocol. All these objects have their own messages associated with them. But what happens, and they're all different. All objects have different capabilities and things that they do. But what's nice is that we don't really have to worry about a master protocol. Every object is different, but can then communicate to the rest of its peers to ensure that we're synchronized.
So it's rather, the fun part of it is a little bit like the web in the sense that when you go somewhere that you don't have the stuff, it comes to you like a web page does. Unlike the web, though, you don't just get a copy. You get a copy that's part of this massively parallel real-time transaction stuff, so that when you do stuff to it's reflected in what you might call psychological real-time to everybody else. And people are interested in how that works. We'll explain it a little bit later.
Okay, now what I'm going to do is go into a true portal. This is our vision of Mars. And what's nice, remember, this is a kind of a window, a door into that space, but I can actually move it around, kind of like the mirror was, except I'm looking into another space. Well, we think of these as the links into another page, if you will, except it's live. And what I can do is literally drop into that space. In fact, if I turn around, I should be able to watch Alan come through. There he is.
One thing that's worth mentioning here is I am doing this part of the demo on, we try and use different machines as we go. This is an ultralight. This is a 2-pound machine that is doing my point of view on this system. Dave has got a little bit more of a gunboat kind of machine.
And mine's the one that has the problems. So this is a little robot that we built. It's
I'm going
actually
to get up on top of this rock so I can
Sojourner.
see you.
And what I'm going to do is start it going. And what's nice is I'm literally controlling both versions, and I can drive it around. Notice, by the way, I should point out one thing. This is all written in Smalltalk. We're using OpenGL at the bottom, but the rendering engine that I wrote is 100% Smalltalk, or Squeak, which I find, I was just totally impressed by what I could do. It allows you to think in a completely different and very powerful way. I didn't learn this, learn how to program Smalltalk until about a year and a half ago. So anyway, that's that, but it shows that a remote control of that object. Next, let's go to the flag world.
Okay, you go your way and I'll go my way.
Yeah. Here's another portal, and what I'm going to do is go through this portal to yet another portal. over here. And what we have is a little simulation running on top of that. I'll close it. Okay. And I'll watch you come down the stairs. This little escalator. This is actually a little tribute to Scott Fisher and Warren Robinette's work at NASA. Who that was, I don't know if you've ever seen that work, but that should be included in Alan's presentation.
It's too recent.
Yes. That was the 80s.
Okay. Go down.
Over here we have a little flag. I'm going to show you there. This is actually a mass spring simulation. It's not a pre-canned thing. And actually what I'm going to do is release the flag just to prove that. And I'm going to crank it back. So they're really actually calculating the little masses and springs.
This is like that particle system, except they're connected by springs and they're pulling fragments of the flag textures around.
So
I should give you a little spin, shouldn't I, David?
So what Alan's doing right now is he literally, I'm on a little carousel, and he just started spinning it. And interestingly enough, we didn't program that explicitly. All that's happening is I happen to be on top of something that's moving, and whatever I happen to be on, I just sort of stick to, and he's changing it around someplace else, so it just works.
Okay.
All right, next up, we're going to go upstairs to a little underwater environment. This is our other collaborator, Andreas Robb, a brilliant hacker. Actually, he was the person who ported Squeak to the PC. And in here is a little underwater space. What's interesting, actually, Alan, when you come in, I'll watch you.
I should mention here that for people who followed the vivarium stuff that we did 15 years ago or so, this is the modern instantiation of it. So I'll come in, plop, I'll turn it into a fish.
Okay, so what I'm going to do here is there's not enough fish. I'm going to create my own. So I need to grab a little paint package. And what I'm going to do is literally draw a little fish, like so. Give it a little bit of an eye, and a little bit of color there. And then paint that, and then
So what's going to happen here, by the way, is originally the work of Takeo Igarashi, who's now a professor at the University of Tokyo, was done for his master's thesis, I think, and it's pretty darn cool. Go ahead.
What I just did, this is the fastest and easiest 3D design tool you ever saw in your life. Wow. Now Alan's going to make something similar. He's going to add a little seaweed to it.
Yeah, so I should come over here. I'll do the same kind of thing. I'll go get a drawing tool here, and I'll do a much harder problem for this program, which is what do we call these things?
Seaweed?
Seaweed. So you imagine now the system is going to, basically what it has to do is it has to take these planar things that I'm painting and figure out the major and minor axes all over the thing regardless of what it is, and then use those as a way of spinning out the tiling for the thing. So this is, we'll have to think just a little bit here on this one. I couldn't actually believe that this would work. So of course I never even tried to do it. Wasn't it your kid?
Yeah.
Dave has a kid, so here it is.
And it's coming over here. The thing to notice also is everything we make is automatically copied over. So I've got, I'll grab this and move it around a little bit.
Actually, it's not really copied, it's actually recreated.
Right.
Because this is a replication architecture.
So what we've done, it's a shared, I said earlier, this is a collaborative environment. It's a broadband conference call.
All of these things are scriptable just the way I showed you. I'm not going to do that right now. But basically, it's all scriptable. And while you're in the routine, one thing I should do before we get out of there is just, this is kind of fun. Squeak has its own browsers, this may now look like a web browser, but we actually put the documentation for this stuff out on the web. And so I'm actually chugging through the actual documentation about how to draw your own fish here, which is sort of set up as a kind of bulletin board.
That's HTML.
That's HTML.
All right.
Okay, let's get out of here. We're doing well.
Yeah. I'm amazed. Now we're changing it out.
Now we have to, let's see, let's close up that guy and then let's go into the David world.
That's me.
I'll close this guy. Oh, you
Already
did. Okay, go ahead.
So this is another little world, just kind of show that we can do a little more
Serious
hefty.
environments.
And it knows I'm following terrain. There's ignore the texture glitches. What I'm going to do is go on top of that aqueduct. And
I'm just sitting up here so we can see Alice when she gets to the top. There she is.
So here I am. And
So the jump. We will, but I think you should go all the way to the end and jump into the pool.
okay. There's our. By the way, just one of the things about 3D spaces is virtual spaces is distance doesn't mean anything. That window over there is pretty far away, but if I just give it a click, I'm right there. And notice I got there really quickly. In fact, I'll jump out here. All of these windows, if I step back, look like icons, and you can just jump to them. Anyway, just another nice, cool thing that, you know, once you start building these 3D environments and actually having something as powerful and useful as this, you have all kinds of things that emerge out of that. We finally have a system that's really good enough to do some really powerful experimentation. You can pick the windows up and carry them around with you. I guess that's it. That's about it.
So I'm going to, hang on, I want to put a little more context here. So let's see, number 3.
Well, we also have voice
So we're
communication.
switching back. I think it's over there, but yeah. Yeah, there's internet, telephony. You have to have telephony in order to do real collaboration. You just have to be able to, because you're using your hands for doing stuff. Okay, so just 2 last things. One is that this is an interesting example of basically the Smalltalk that was last used at Xerox PARC, updated to the 21st century graphics and stuff. No intellectual interest whatsoever since about 1975, except that pragmatically, it should be of some interest because, for instance, unlike Java, it runs exactly the same on every machine, identically, guaranteed by a porting mechanism we actually wrote up 20 years ago. Java didn't use it, and it's just simply not possible to implement something to a paper spec and validate it with benchmarks and have it run everywhere. You really have to generate the ports mathematically. Squeak is its own operating system. That's another thing. We don't try and use native tools. The exception here is the OpenGL stuff, but everything else is part of the graphics. The object system is kind of fun in that characters are actually objects. So this is kind of a little more of a sketchpad way of thinking about things. One of the things that's worthwhile showing is that there's no presentation application here because if you have multiple desktops, and that's what we did have at Xerox PARC, then here are all the desktops that are part of my system here. Each one of them is a full unit of work, and I have a sorter for each talk that I give, so I can decide what to show next maybe I want to show this late binding slide next. And that just becomes part of the O'Reilly conference talk here. Why go to something weaker like PowerPoint to try and show stuff? This is an interesting example of what I consider to be a really negative, retrograde way of looking at things, which was the reemergence of applications and separate operating systems after I thought we'd safely killed them in the 70s. Sort of like using the wrong kind of wood for Dracula's steak. Key idea here, which is still not the main idea in this is what to do until software engineering gets invented, do late binding. Virtually every piece of software done today is done as early binding through manipulating text files, compiling. Java still has a hard time adding code to itself while it's running, for Christ's sakes. So if we go back to Peter Deutsch's Lisp of 40 years ago, it did not have that problem. Should be able to do everything dynamically. The system should be able to safely maintain its own environment while you're debugging its own environment. Should be able to make every change in less than a quarter of a second, and so forth. And the reason is we just don't know how to do software yet. So basically, when you have the disaster, you finally realize, oh, I should have done this back here. If you've got a late binding system, you can go back and change it. If you've got a typical C-based, C++, Java, whatever other systems people use, you just can't do it. So this system is interesting in its antiquity of these late binding ideas. And we're showing that it can run just as fast as anybody's nervous system requires. And one last thing is, because it's a dynamic object system, all the objects are alive, so we can ask it questions as though it were a database. And the most interesting question, I think, at this point is how large is the total code for the entire operating system and all the stuff that you've seen in bytes. I'll just ask it to count this right now and compute it. And the answer is 2.8 megabytes for everything. How many lines of code are there in the system? Well, the operating system and all the applications and everything, it's about 230,000 lines of code. Now, from our standpoint, we think it could be about 20,000 lines. So we're about a factor of 10 away from what we think the actual mathematical entropy of a system like this could be if you were doing the right things. We're going to take a shot at this 20,000 lines of code next year. And then the last thing is, since everything is an object in this system, we can ask it how many objects are there. Now it's counting all of the objects that it itself is using right now. There's about 1.8 million objects. So that's the end of our presentation, and thank you very much.